All right, this is 2012 number 5. This is talking about intermolecular forces. This question, kind of all the way through, the little Lewis structure drawing at the end. It gives us bromine. Bromine's a liquid at room temperature. It's blue on the periodic table in the classroom. Iodine is solid at room temperature. These guys are both turning into gas. So iodine here is subliming. The bromine's vaporizing. It gives us delta H's for both of those things. And it's going to reference those delta H's in the first part of the question. So it kind of tells us the start of that. Perfect. Explain why. So here's question number 1. Explain why delta H for the formation of iodine gas to iodine solid is greater than from bromine gas, the bromine gas from liquid. Explain the type of particle interactions involved. So it's asking us to explain this delta H here. So why, it's really asking, why does it take more energy to take that solid and rip it apart than it does to take the liquid and rip it apart? And so if we're talking about particle interactions here, we are talking about intermolecular forces. So 5A, and you could talk about sublimation takes more energy to go from a solid state to a gaseous state. That's fine. I would talk about it this way. I would say both molecules are nonpolar. Talk about the similarity there. They're both nonpolar and have dispersion forces holding them together. The dispersion forces in iodine are greater because they have more electrons and therefore more polarizability. So it takes more energy to break them apart. I gotta work on my handwriting. That's 5A. It's like writing an essay. 1.5 sentences, right? I got 2 in there, so somewhere between 1 and 2 sentences. If it takes more than that, it's probably too much. So there's 5A, that's it. 5B says predict which of the 2 processes shown in the table has the greater change in entropy. Justify your prediction. You got to refer to entropy here, right? And so which one has a greater change in entropy? This one's going from liquid to gas, so there is an increase in disorder there. This one's going from solid to gas, so there's a greater increase in the randomness of the particles. So iodine has a bigger increase in entropy because the particles move from a very structured solid to the particles moving very randomly. I would put the solid iodine had more original order than the liquid bromine. Talk about both pieces in each of those answers, both the iodine and the bromine. That's part B. Bigger increase going from solid to gas has a bigger increase than going from liquid to gas. That's part B. And part C says iodine and bromine can react to form the compound IBR. Predict which would have the greater molar enthalpy of vaporization, IBR or BR2. This is kind of talking right back up to the initial question, except now we have these two compounds we're comparing, and so we need to look at intermolecular forces again. IBR here is going to have the greater molar enthalpy. Why? Because it's polar. It has dipole-dipole forces, where bromine only has London dispersion forces. So that's my explanation. IBR has greater delta H because it has dipole-dipole interactions that are stronger than the dispersion forces of bromine. That's it. Talk about both of them. Talk about which one's stronger and which one's weaker. Good? Good. We're almost done with the essay writing. Hang on. It says experiments performed where the solubilities of iodine in different solvents. Forgive me for that shadow. Experiments performed to compare the solubilities of iodine in different solvents, water and hexane. Student adds 2 mils of water, 2 mils of hexane to a test tube. These guys are immiscible. That means they don't dissolve in each other, so we see 2 layers observed in the test tube. The student drops a small purple crystal of iodine in the test tube, which is then corked and inverted several times. The hexane layer becomes purple, while the water layer remains virtually colorless. Explain why the hexane layer is light purple while the water is colorless. Your explanation should reference the relative strengths of interactions of molecules of iodine and the solvents water and C6H14 and reasons for their differences. Holy moly. So this is about solubility. Iodine will dissolve in the hexane because they are both nonpolar and it doesn't take much energy to separate their IMFs. That's why it dissolves in the hexane. Good. And then talk water. Water has hydrogen bonding. Which takes a lot of energy to break apart. And therefore won't dissolve the nonpolar iodine. It's kind of, you got to mention water's hydrogen bonding in there. Polar and nonpolar are good if you can reference the polar and nonpolar in that answer to part D. My hand's getting tired, all this writing, crazy talk. And then we've got a couple left. These are a couple quick ones. The student adds a small crystal of potassium iodide to the test tube. The test tube's corked and inverted several times. And we get this ion, this iodide ion, that reacts with iodine and forms I3. It tells us it's linear, that's helpful. It says draw the complete Lewis dot diagram for the I3. I don't think you're going to have to draw a Lewis structure. They've kind of hinted at the fact that you wouldn't. Man, one of my smartest kids came in after the test was over and they released the questions, of course, and forgot to put brackets. If this is an ion, you've got to put brackets with the charge on it. We have those 3 iodines. They each have 7 valence electrons. That's 21 plus that one is 22. There's 11 pairs here. And so we have 1, 2, 3, 4, 5, 6, 7, 8 pairs, 9, 10, 11 pairs, right? And you could do those as dots. But we've got 5 domains there with 3 lone pairs, right? This is head and feet in a triangular hula hoop, and the hula hoop is gone. And so it's just head and feet. That's what gives it that linear shape. That's what that structure looks like. Good? And I'm running short on time too, so I didn't do all the little individual dots. You could put dots here, that's fine, and dots around those. It's probably better that way. But that's the Lewis structure. It says in which layer the water or the hexane with a concentration of I3 be higher. This guy has a charge, right? So that ion charge in part 2 here, you would say the ion is going to form ion dipole interactions with water and dissolve. I would put the hexane ion induced dipoles will be too weak, so I3 won't dissolve in C6H14. Talk about these interactions. Water is charged, right, because it's polar, and so it's going to dissolve that charged or polar I3. This guy is non-polar, so it won't dissolve those. Now, it does have an ion, and that ion will induce some dipoles out of the C6H14, but those are going to be weaker interactions than the ion dipole interactions that are already established with water. That's it, 2012. That is number 5. Have a good one.